Hello, my name is Katie Little, and for my Unit 4 project, I'm here to talk to you about reflexes. And I'm talking about reflexes because I feel that they illustrate a lot of different concepts of the nervous system that we've been covering in these 4 chapters. So let's begin. What is a reflex? A reflex is an involuntary response by a muscle or a gland to a stimulus, and that response is carried out via the nervous system in a pathway called the reflex arc. So, reflexes have 4 main characteristics, although there are different types. They all have the same 4 characteristics. They are not spontaneous. They do require stimulation, and that's good because we don't want reflexes happening randomly. We want it to be a response to a stimulus. And reflexes are fast. They are very quick, and that's good too. If you're burning your hand on a hot stove, you want to pull it away as quick as possible, and reflexes help you do that. Reflexes are not voluntary. Although some reflexes are under our conscious awareness, we are aware that they are happening, they are not under our conscious control, no reflexes. And again, that's a good thing. You don't want to have to think before you do a reflex because a lot of reflexes are essential for survival. And then reflexes, lastly, they are stereotyped. They occur basically the same way every time. Also a good thing. If you get hit in the knee, your leg should kick out, not your arm. So, those are the 4 main characteristics of reflexes. And before I get into it a little deeper, I would like to talk about the divisions of the nervous system. So just a quick review here. So we have one nervous system in our body, that's important to remember, but there's a lot of different divisions that do different actions. So our nervous system is divided into the CNS, the central nervous system, and the PNS, the peripheral nervous system. And the CNS is the brain and the spinal cord. And the PNS, the peripheral nervous system, that's everything else, all nerves throughout your body that are not in your brain and spinal cord. And the peripheral nervous system itself has a couple more divisions. There's 2 that are going to be very important for what I'm talking about today, the somatic nervous system and the autonomic or the visceral nervous system, visceral meaning internal organs. The somatic nervous system includes skeletal muscle, skin, and tendons, and it includes sensations that we are aware of and things that we can voluntarily control. So skeletal muscle is what's allowing me to do this. So any muscle movement that I can consciously control, things I am consciously aware of, like pain. And then the autonomic nervous system, that controls everything else. So digestion, glandular secretion, breathing, heart rate, blood pressure, blood sugar, kidney regulation, a lot of things that are very essential for our survival, but they are not under conscious awareness. So, and not under conscious control either. That's important. And the somatic and the autonomic nervous system are both divided into sensory and motor pathways. Some people include sensory only under somatic, but I think it makes more sense to include it under autonomic too. And sensory is often called afferent, and motor is called efferent. So sensory is interpreting a stimulus and sending a signal via the nerves toward the central nervous system. So afferent, away from the outside world and toward your central nervous system. And then efferent, motor pathways, they go from the central nervous system out to the rest of the body. So important to remember, especially when we get into reflexes, because there are 2 main kinds of reflexes. There are somatic and autonomic reflexes. And while they are quite similar, they do have some important differences that I'm going to talk about next. So, a reflex pathway, I mentioned that it's called an arc, and it goes about in a circle, really, or more like a U shape. All reflexes have this same arc pathway, although it might look a little different. So, a reflex starts with a receptor, and this receptor could be something in your skin to detect pain. It could be a baroreceptor in your arteries to detect blood pressure, and in your eyes to detect light. It could be a lot of different things. But it takes a signal, either pain, heat, pressure, and it will send this signal to the central nervous system via an afferent nerve. So again, a sensory nerve. And once the reflex gets to the central nervous system, it gets to an integrating center, which could either be in the brain or in the spinal cord. Some reflexes are referred to as spinal reflexes, but this isn't totally accurate because a lot of reflexes do go up at least into the brain stem. And the integrating center often involves one or more interneurons, so neurons that connect afferent and efferent neurons. But there's usually not that many because, remember, we want a reflex to be fast. And if you have all these synapses along the way, it does slow it down. So integrating center is pretty small. So once a decision has been made as to what to do about the stimulus, the signal will travel down an efferent nerve to an effector. And this effector is different depending on what type of reflex it is. For somatic reflexes, the effector is a skeletal muscle. For autonomic reflexes, it could be a couple different things. It could be smooth muscle, cardiac muscle, or different kinds of glandular tissue. So, got the basic reflex arc right here. And I want to talk to you a little bit more about the differences between autonomic and somatic reflexes. And this is a figure from Rice University's website, which I think shows that pretty well. I don't know how well you can see here, but I'll explain it. It shows the efferent pathway for an autonomic and a somatic reflex response. And they show just the efferent pathway really because the afferent pathway is quite similar amongst the two. You have a receptor, you get a stimulus, it sends the stimulus towards the central nervous system. There's an integrating center, and then where the difference lies is in the effector, or in the efferent pathway and then the effector. So in the autonomic nervous system, you have, in the efferent nerve, it's not just one neuron fiber, there's a couple, and they synapse along the way. And they synapse at a place called a ganglion. And so because you have this extra synapse in the efferent pathway, it does slow things down a little bit for the autonomic reflex. Although they are fast, they're not as fast as somatic reflexes usually. And so you have these efferent nerves, neuron fibers, and then the target effector organ in this case is a smooth muscle. So that's quite different from a somatic reflex, which would have a skeletal muscle as the effector. And remember, this could also be cardiac muscle or a gland. And notice too that the efferent nerve for an autonomic reflex does not necessarily end at a synapse. There is just a varicosity, a little bulge, where vesicles, remember them, synaptic vesicles, they release neurotransmitter out to the effector, but not necessarily ending at a synapse. Somatic efferent pathway, in contrast, after you have the interneuron, you really only have one efferent neuron, so it goes a lot quicker because you don't have that delay at a ganglia. And the target effector is a skeletal muscle. And notice that the efferent nerve does end at a synapse, and at this synapse there's neurotransmitter being released from synaptic vesicles, and depending on what that neurotransmitter is and the receptors on the target organ, that determines the response. So another blast from the past is that there are two postsynaptic potentials. There's the EPSP and the IPSP. The EPSP is excitatory postsynaptic potential, and the IPSP is the inhibitory postsynaptic potential. And the EPSP causes depolarization in the effector, and that will cause a response because it's becoming more positive, it's closer to threshold, it can cause an action potential, or in this case, contraction. And the IPSP, it does the opposite. It causes hyperpolarization, such that the next cell becomes more negative, and that inhibits contraction, as we'll see. So, pretty interesting, and that comes into play in several important reflexes. And so I just want to give you one example of an autonomic reflex, and this is the baroreceptor reflex involving the heart and the carotid artery. And so this is a figure from Saladin, which is our anatomy textbook, figure 15.1. And you'll notice that in this figure, this person's blood pressure, for whatever reason, is too high, higher than it should be. And so there are receptors, baroreceptors, that can detect pressure in this carotid artery, in both, but I think they're only showing one. And these sense that the blood pressure has gone up too high. And so what happens is a signal is sent along an afferent nerve. In this case, it's cranial nerve 9, the glossopharyngeal nerve, which we learned in chapter 14 about the brain. And this signal is sent via the afferent nerve to the medulla oblongata, so the brain stem. And there's interneurons here that make a decision, and then they send a signal via an efferent nerve, which in this case is the vagus nerve, cranial nerve 10, And when that gets to the effector organ, which is the SA node of the heart, it causes the heart to beat slower, and then that decreases blood pressure. So reflexes are really important in maintaining homeostasis, because remember that your blood pressure, or any metric in your body, is not always going at a straight line. It's not the exact same 120/80 all day. It does fluctuate a little bit. If it gets too high, a reflex such as this one, an autonomic reflex, will cause it to decrease. And if it gets too low, there's other reflexes that can bring it back up again. And so dynamic equilibrium, it constantly fluctuates, but just a little bit. So autonomic pathways like this are very essential to maintain survival. You don't want your blood pressure to get too high. So, just a sec.